verification 2 will be about verification programs under the release class.
Okay, thank you. So this is a joint work with Parosh from Uppsala University and Jatin and Krishna from IIT Mumbai. So in this work, we are interested by the verification of a class of concurrent program where the communication is done through shared memory. And usually programmers assume this classical interleaving semantic or the sequential consistency semantic where the execution of different processes or threads are interleaving, and also the operation are assumed to be done in atomic manner. So let's take an example which is similar to the Dekker mutual exclusion protocol. Here we have two processes, P1 and P2, and P1 will set X to 1, means that he would like to enter to his critical section at line 4, and then check the value of Y. If Y is equal to 0, this means that the second process didn't request to enter to his critical section, then the process P1 can proceed and start working or running his critical section. Now the same for process P2, but we interchange the role of X and Y. Now under this sequential consistency semantic or SC semantic, we can see that one of this process will succeed to set either X to 1 or Y to 1, and therefore he will block the other process from entering to his critical section. So this is an example of a run where the first process will set X to 1, then will read the value of Y is equal to 0, and therefore he can start executing his critical section. And then the second process will set Y to 1, but he will not be able to read that X is equal to 0, and therefore this mutual exclusion property is preserved for this program. Now, when we run this program under modern processor or compiler, this program will exhibit more behavior. This is due to this reordering of instruction and use of cache and buffer. And this is done for performance reason. So our program will exhibit more behavior than the sequential consistency. And this is captured by the framework, what we call weak memory models. And in this work, I will talk about the verification of program running under the well-behaved fragment of C11, which is called the release acquired fragment. Now, for the release acquired fragment, all the writes are released, and a write release means that anything coming after this write should not, anything which is before that write should not be reordered with this write. And read acquired means that anything coming after this read cannot be ordered with the read acquired. But we allow that this read overtake that write, for example, like in TSO. Now, and this rest of the talk, I will assume that all the writes are released and all the reads are acquired. I will not mention it anymore. So if we take this reorder and we take our previous example now, we can see that we can reorder this read here of the second process with that write. And therefore now we have another execution of our program where we violate this mutual exclusion property. So, and this leads to bad behavior. Now in this paper or in this work, we are more interested by the verification of program running under the release acquired semantic. And more precisely, we are interested by the verification of safety property. And as we know, safety property verification can be reduced to the verification to the reachability problem. So we are given a state of in our program, can this state be reachable under the release acquired semantic? So the first question that we have asked ourselves, is this problem decidable? And if it's decidable, what is the complexity? So as we know that if we take finite state process, this problem is p-space complete when we are running under SC. Now this is not trivial when we run under release acquire, because what we have due to this reordering now, the set of behavior is not regular anymore. And what we have showed, surprisingly, that the state reachability problem is undecidable for release acquire. And the proof is done by reduction from the post-correspondence problem. I will not go into details due to the time limit for this undecidability proof. So then what can we do? So, and there is this bounded context analysis, which has been proposed by Shaz Kadir and Jacob Rehoff in 2005. And the idea there is just to look or to analyze runs which can be split into a bounded number of contexts, and where in each context there is only one active process. And then we try to adapt this definition to the release acquired, But our proof still goes through, and we have still undecidability for this bounded context switch. So then we try to have a better under approximation. Okay. Right. Yes. So we tried to have a better under approximation where we have a new notion which is called view switch. And so we bound the view switch. And this notion of view switch coincides with bounded context under the SC semantic, but it's different under the release acquire semantic. I will explain it later on. I will go into details. Then we showed that for reachability, when we restrict the reachability problem within a bound on the number of view switch, we can reduce this reachability problem to the SC reachability problem within a bounded number of context switch. How we do it? We do some code-to-code translation with a polynomial overhead. And then we have implemented a prototype, and what we observe is that few number of view switch are sufficient to detect most of the bugs. So the rest of the talk, I will briefly describe what is the operational semantic of release acquire. Then I will show main or high-level idea of our reduction to show it's decidable. And then finally, I will give some comments about our experimental results. So let's start by the operational model of release acquire. Under SC, we have the process communicate through shared memory, and each process will read the last written value on each variable. And the release acquire, now the memory is a pool of views or message. And each message is a written write operation. Here, for example, X has a value 1, and we have 2 timestamps or logical clocks when 1 per variable. And for example, here the timestamp of X is 4, and the timestamp of Y is 1. And then for the configuration of the process, we have also his own local view of the memory. For example, his timestamp for the variable X is 3, and his timestamp for the variable Y is equal to 2. Now, when this process tries to do this first read operation of the value of X, what he does, he will discard first all the message and the memory that concern the variable Y, since he wants to read the value of X. And once we have done this, we look now to the timestamp of X, or the view of that process for the variable X. And here we have 3. And we compare to the remaining message. And we see that the timestamp for that process is 3, and we compare it with this one, which is X is equal to 3, and the timestamp for X is equal to 1, which is smaller. This means that he cannot read it. And therefore, we cannot read that the value of X is equal to 3. Now, if we compare with the X is equal to 1, we see that the timestamp is 4, which is larger than 3, and therefore now he can read that the value of X is equal to 1. So before reading, he needs to update his view of the memory now. What he does, he will take the maximum of the timestamps of these 2 views. So now the new view of that process will be 4.2. And then once it is done, he will set the local register A to 1. So this is the read operation, how it works. Now for a write, he will try to make a new copy or local copy of the message that will be sent to the memory. So first he needs to find a new timestamp which is larger than its own timestamp for X, which is 4, and it has not been used in the memory already. So for example, here I can choose the new message with a timestamp 5 for X, and this will be added to the memory. And finally, the last read operation on Y, we do as we have done for X. We look only to the message concerning the variable Y. And then for the variable Y, we compare this timestamp 2 to the timestamp of this message concerning the variable Y. And we see that 2 is larger than 0, and therefore we cannot read that the value of Y is equal to 1. And we can see that also that 7 is larger than 2, and therefore we can read that the value of Y is equal to 5. And so we have that now the new value of B is equal to 5. And this is a rough idea how release acquire fragment works. Now I will use this example as a running example to explain this view, our under approximation. And therefore I will go briefly over it. So the first process, he would like to read the value of x. So now we have only one message on x, and then he will read that the value of x is equal to 0. And then he will write to the variable 1 the value 1, and so he will add new message in the memory. Once we have done this operation, we move to the second process. He would like to read the value of y. Now he has the option, either reading y is equal to 0 or y is equal to 1. So let's assume that he chooses to read y is equal to 1. And then he will do two write operation, setting x to 1 and then setting x to 2. And then we resume the execution of the first process. He would like to read the value of x. And then now his timestamp for x is equal to 0. So he can either read that the value of x is equal to 0, or the value of x is equal to 1, or the value of x is equal to 2. So let's assume that he picks that the value of x that he wants to read is 2. And this is a possible execution when we have multiple processes. So now I will go through this reduction of the analysis of reachability under view switch bounded to the SC reachability problem. So first, what does mean view switch? View switch happen when a process reads a value that has been written by another process. For example, here we see that this process reads the value of y is equal to 1, and this has been written by the first process. So this is a view switch. Now we see here also we have a view switch, another one, when this process reads the value written by the second process, which is x is equal to 2. Now view switch is not only, we are not only reading that value really, because release acquire is like causal consistency. So when we read y, we also read some value of other variable that are causally related to y is equal to 1. For this example, we don't have such behavior, but in reality, we need to read, let's say, a summary of the memory when we do some view switch. So, and this is a two-bounded run, and then what we do is just we are interested to restrict reachability to only k-bounded run. And what we show that the k-bounded run reachability problem can be reduced to reachability under a C within a bounded number of context switch. And this is reduction is done code to code. So we have input program and we try to rewrite it and then adding few number of variables, and then we analyze the instrumented program. And as a corollary of this, we have that the k-bounded reachability problem is decidable for finite state programs. So what is the idea here? The idea is the following. Since we are bounding the view, in some sense we are bounding the number of essential, what we call views in the memory. For example, this x is equal to 1 will not be read by the first process, and therefore we ignore it when we don't add it to the memory. But it's still read locally by that process that generated. Now what we do is just we guess all this essential message in the memory. And once we have done this, we proceed in two steps. The first step, what we call locality, and the second one is validation. Locality, what does mean? We try to have interfaces about the phases of the run of each process. For example, this phase here, when we run this first process, we start from a local copy of the initial memory, and then we compute what is the resulting value of these variables. First, this is the new local memory of that process. And then we have x is equal to 0 and y is equal to 1. And then we also compute what kind of message that thread or process will provide to the second one, which is at some view switch. And here he will only provide that the value of y is equal to 1. So now when the second process will start, he will do a view switch. So he will now update his own memory. So he will set y is equal to 1, and he will start running locally, and then he will compute what is the resulting memory that he will have, and also what is the kind of message here he will provide to the first process and the next phase. And therefore here we'll have x is equal to 2. So then we combine x0 and y1 with this x2 to compute the new local view of the memory, and then we run the first process. Now, as you can expect, we can do this locally. We guess all these interfaces by guessing the essential views in the memory. And once we guess them, we can run independently the first process from the second one. So, and then we verify that this behavior can be done by that process. He will start from this local memory, reaching this one, and providing that the value of y is equal to 1. And this can be done under SC. We do the same for the second process, and then we just run it and verify that these interfaces are correct. Now, once we have done these two checks, now we need to verify these interfaces are compatible, and then we do just check that this initial memory plus merged with y is equal to 1 result in this new local memory, and then we do the same for the other one. And this is mainly the code translation that we are doing. So I will go quickly over the experimental results, and we have implemented a prototype which is called VBMC, and this prototype is using as backend tool for concurrent program CBMC. And then what we have done, we just run it over a number of litmus tests for sanity check, and also we run it on some concurrent benchmark, mainly mutual exclusion protocol. And what we observe that we need only view number of context or view switch here for bug detection. And also we run it with, we compare the result with different stateless model checking tools, Tracer, CDA checker, and RCMC. And the two techniques are orthogonal. It's hard to, let's say, have a conclusion out of this comparison. But what we observed in some sense that this bounded view switch is orthogonal to stateless model checking. In some cases it performs better, in some cases stateless model checking techniques are better, and therefore can be used in complementary manner to this to stateless model checking techniques. So we reach the conclusion. In summary, we tried to verify program running under release acquire. We showed first that the reachability problem is undecidable, even if we bound the number of contexts, and therefore we came with new suitable under approximation technique, and this technique is equivalent or coincide with bound context under SC, and then we have showed it's decidable when we bound the number of view switch. So, thank you.
Hi.
Hi.
Thanks for a very nice talk. So from your results, I understand that you can have a run with a bounded number of context switches, but infinite number of view changes.
Yes,
Could
exactly.
you, like, give some intuition? How does the run like that look like?
Because in some sense, when you say that one process is active, this means that he can, in some sense, our memory is a pool of messages. And then when he is active, he can read many. Let me try to go through. So for example, this one, when he tries to read the value of x, he can first read x0, then he reads x1, then he reads x2. So you see that he has done two view switch already here. So he can read unboundedly many number of messages in the memory.
So if the reads are inside a loop,
yeah. Yes, exactly. If the reads are inside the loop, he can read what exists in the memory already now.
Thank you.
You're welcome.
I think perhaps we've got time for one more question. If no one else is going to grab the slot, I will.
So I was just wondering if you could comment on the scale of the problems that you're solving with the tool. I mean, it looks like they're mostly mutual exclusion protocols. I mean,
we can run, in some sense, we are bounded only by our backend tool, which is CBMC. We are only adding few copies of the shared memory, and then we translate we give everything to CBMC.
Right.
So in some sense, if the CBMC cannot do it, we will not be able to do it.
Right. That makes sense. Thank you.
Yeah.
We thank the speaker once more.